Well, the first part of this question is to make use of the method of mathematical induction to prove that summation equation, where I'm going to first let Pn, where my proposition, be that equation. So it is summation of r is equal to 1 to n of r 2r squared plus 1. This is supposed to be equal to half n of n plus 1 of n squared plus n plus 1. Okay, and for this mathematical induction, it is supposed to be true for all n that are positive integer. Okay, the question didn't mention this. How do I know that I'm supposed to let n be all positive integer? Because looking at the n over here, where the summation starts from 1 and it ends at n, so the smallest n can go is actually 1. Okay, so since the question didn't mention anything, I will just assume it to be all the possible, the maximum possible values of n. Okay, so n is going to start from 1. Okay, to start off my mathematical induction, I'm also going to go for n is equal to 1. For that smallest possible n, I want to prove that this proposition can be true. Okay, so looking at the left hand side of P1, left hand side is summation of r is equal to 1 to 1 of r 2r squared plus 1. So this is 1 of 2 plus 1, this is equal to 3. Okay, next I want to look at the right hand side of this P1. The right hand side, okay, replacing all the n by 1, it is going to be half of 1, 1 plus 1, and 1 squared plus 1 plus 1. Okay, so 2 and 2 can be cancelled. With this, I'm going to be left with a 3. It is the same as the left hand side. Okay, so what we can conclude here is that P1 is true. Okay, since P1 is true, okay, then it allows me to make an assumption. I'm going to try to assume, without proving, I'm going to assume that Pk is true. So I'm going to assume, okay, that Pk is true, okay, for some k that is also the same range of values as n. Okay, so for some k to be also positive integer, okay, because we are not looking at any possible values of k, it has to be k that belongs to n. Okay, so it belongs to the same set of value. Okay, that means we are assuming that summation of r is equal to 1 to k. Okay, it is r of 2r squared plus 1. This is 1 over 2k, k plus 1, and k squared plus k plus 1. Okay, with this assumption, what we are trying to do is to prove that pk plus 1 can be true because this is true. Okay, let me write down my aim first. Okay, like what we were saying, it is to prove that the pk plus 1 proposition is true. Okay, that means we are trying to prove that summation of r is equal to 1 to k plus 1 of r 2r squared plus 1. Okay, this can be equal to half of, replacing all the n here by k plus 1. Okay, so half of k plus 1. K plus 1 plus 1, so this is k plus 2. Okay, then this replace it by k plus 1. Then this replace it by k plus 1 plus 1. Well, if I were to just simplify this a bit, this is k plus 1, k plus 2, and what we have here is going to be equal to k squared plus 3k plus 3. Okay, so this is what I want to prove, and yet I'm not trying to prove that this is equal to this directly. What we want to do is to establish a relationship. A relationship between the pk proposition and the between the pk plus 1 proposition and the pk proposition. Because what we intend to do, what mathematical induction allow us to do, is once we have managed to establish this relationship between the pk proposition and the pk plus 1 proposition, we want to establish that as long as pk is true, it's going to induce for me to conclude that pk plus 1 will also be true. Because once we can establish that kind of relationship, then with P1 that is true, it automatically tells me that P2 will be true. If P2 is true, then P3 will be true, and so on. Okay, so let's try to prove this relationship here, okay, between Pk and Pk plus 1. And to do that, let's go for the left hand side of Pk plus 1, where I'm going to work on the summation of r is equal to 1 to k plus 1 of r 2r squared plus 1. What I want to do is to bring in the assumed truth of pk. Okay, so to do that, I'm going to break up the summation notation. Rather than summing from 1 all the way until k plus 1, I'm going to sum from 1 until k, okay, of the same expression. So 2r squared plus 1 plus that last term, which is missing out from here, but it is still here, which is the term when r is equal to k plus 1. Okay, so that is that term, replacing all the r here by k plus 1. So k plus 1 and 2 times of k plus 1 squared plus 1. And now this is where I'm going to make use of the assumed truth of the pk proposition, because this I have already assumed that it is this. Okay, please take note. I didn't really prove that it is this. Okay, I'm just assuming that it is true. Okay, so let's say that it is really true. That means this can be replaced by half of k plus 1, k squared plus k plus 1. Okay, plus this is k plus 1 multiplied by this. This, if I were to expand, I'm going to get a 2k squared plus 4k plus 3. Okay, what I'm going to do is I'm going to try to manipulate this so that this can ultimately become this. Because if it is true, that means what I've proven is that as long as the previous proposition, okay, this is the pk plus 1 proposition that I'm trying to prove. So as long as the pk proposition is true, it's going to cause the pk plus 1 to be also true. Okay, so let's see whether we can continue to work out on this to make sure that to see whether it can become an expression that looks like that. Okay, one trick that we have mentioned in our outline, it is that rather than expanding, okay, sometimes it is better for me to consider the process of factorization. Looking at what I want to prove, there's a half and a k plus 1. And the good thing is there's a half and k plus 1, and there is a k plus 1 here, okay? So what I'm going to do is I'm going to directly take out half and k plus 1, okay? I'm going to try factorization, which leaves me with a k and k squared plus k plus 1, and this, it is going to be 2 times, okay, because I factorized out a half of 2k squared plus 4k plus 3. And for what I have here, if I were to simplify this, okay, this is k plus 1, simplifying this, okay, expanding and simplifying. I think this one we have no choice but to expand it. That's why I'm expanding this. Expanding this, I'm going to be getting a k to the power of 3 plus 5k squared plus 9k plus 6. Okay, and this is actually a bit troublesome, okay, because now we need to factorize this. Okay, if I were to, okay, let me just work on this separately first, okay, before I continue with the manipulation. If I were to just look at this, okay, if I were to let fk will be equal to k to the power of 3 plus 5k squared plus 9k plus 6. It will be good if I can just press this into my calculator and let my calculator factorize this. Okay? But if you were to do that, you realize that there's some problem, okay, because my calculator is going to give me part of the solution as, you know, tons of decimal values. Okay, so I got to do this manually. But at least one of the roots that my calculator can tell me is one possible root is k is equal to minus 2. Okay, so k plus 2 is going to be a factor. Okay, so since k plus 2 is a factor, to find the other factor, I'm going to do a long division. So this, okay, I'm going to take this divided by k plus 2, which I deduce from my calculator. Okay, so let's try a long division. This is going to be k squared. So this is k to the power 3 plus 2k squared. Minus of this is going to give me a 3k squared plus 9k. So here is plus 3k. So this is 3k squared plus 6k. Minus of this, I will have a 3k plus 6. And this is going to be a plus 3, and it is 3k plus 6, which is perfect because I get a remainder as 0. It tells us that at least k plus 2 is really a factor. Okay, so this expression can be re-expressed as k plus 2 multiplied by k squared plus 3k plus 3. Okay, so now replacing this by what we have factorized here. Okay, I know this is going to be half of k plus 1. Okay, and what we have factorized is k plus 2. Okay, and k squared plus 3k plus 3, okay, and which is exactly the same as this. This tells me that I have managed to establish this relationship, okay, that as long as the previous term is true, it's going to cause the next term to be true. Okay, let's seal this, okay, with a good conclusion, where I'm going to say that what I found out is that pk plus 1 is true, okay, if pk is true. Okay, so since I've also proven that p1 is true, okay, so by the process of mathematical induction, okay, by the process of mathematical induction, I can see that Pn is also going to be true, okay, for all the n's to be positive integers, because as long as P1 is true, okay, then according to what I have proven here, P2, P3, P4, all will be true, okay, so Pn is true for all the n's that belongs to positive integer.